when we think about the intensity of light emitted by a black body, we think about the sum of all the light emitted for all the wavelengths. So this is a black body curve, the relative intensity as function of wavelength. Then the intensity emitted on the surface is the area under the entire curve. Of course, when we look at the star, which is a black body with our eyes, we're only seeing a small fraction of that area of that light. We're only looking at wavelengths around 500, 550 nanometers and adjacent wavelengths. So if we look at a star with a telescope, the same thing happens. Sensitivity of a telescope may be different than the human eye. For example, certain photographic films are more sensitive in the blue area of the spectrum, and their peak of sensitivity is centered around 450 nanometers, but it is the same idea. You're only looking at a small fraction of the entire light emitted by the star. Now, why is this important? Because when we think about magnitude, we're thinking about how bright a star appears to a given observer, be it the human eye or a telescope. And when we think about the apparent luminosity, which is proportional to the intensity, we're only looking at the fraction of the intensity that you can see, which is a very small fraction of all of the light emitted by the object. So this appears to be a limitation, and we have to specify what kind of magnitude we are looking at when we look at a star. So anything that is seen by the human eye or by an optical instrument that reproduces the sensitivity of the human eye, which means centered around 500 or 550 nanometer, we call that the visual magnitude. So all the magnitudes that you read about stars are by default visual magnitudes as seen by the human eye or by an instrument that reproduces the spectrum of the human eye. Therefore, we would write down M subscript V for visual magnitude. There is an alternative. In many astronomy textbooks, they only use capital V. So capital V or MV is for visual magnitude. Okay, this is the default magnitude seen. So when we talk about the apparent luminosity of a star, visual, we're only looking at the area under the visible center of the visible part of the spectrum, not the entire area. We talk about blue magnitude because this corresponds to many photographic films. The sensitivity is around blue. So the blue magnitude centered at 450 nanometers, and we use M subscript B or capital B. This represents apparent blue magnitude. Then we can think about absolute magnitude. We have the absolute visual magnitude, and we have the absolute blue magnitude. Now, what appears to be a limitation of your optical instrument can actually be used to acquire additional information about the star, and specifically its temperature. So, if we look at a star like the sun, so around 6000 Kelvin, look at the lower blackbody spectrum here. Of course, the peak of emission, the lambda max, is around the middle of the visual spectrum, around 500 nanometers. Now, if we look at a star like the sun using a filter that reproduces the sensitivity of the human eye, so the visual magnitude, we would see that the star is very bright. If we look at the same star with an optical instrument centered around blue, the star doesn't emit as much blue, so it will look fainter in the blue region of the spectrum. So if we measure its visual magnitude and we compare it to its blue magnitude, which one is larger? Take a second, pause the video, and write either bigger or smaller. Be careful. Unpause when you're ready to continue. The blue magnitude will be larger than the visual magnitude because magnitude is a ranking. A large magnitude means faint. Small magnitude means bright. So the visual magnitude for this star will be brighter and therefore a smaller number than the blue magnitude. If we look at a very hot star, 12,000 Kelvin on the surface, it will emit more blue light than yellow light, right? More blue than visual. So we would consider the blue magnitude for this star to be smaller than its visual magnitude. In other words, brighter in blue than in visual. So when we take the difference between the blue magnitude and the visual magnitude, for here, a star like the sun, B minus V will give me something positive. Okay, relatively colder star, brighter in visual than in blue. For the relatively hot star, the blue magnitude is smaller than the visual magnitude. So B minus V will be negative in this case. So if it's negative, it's an indication that it's hot. If it's positive, it's an indication that it's cold. The more positive, the colder. The more negative, the hotter. Now, this magnitude scale, blue and visual, have been calibrated in a way that the difference is exactly zero when the temperature is 10,000 Kelvin. So the blue minus visual magnitude, which is called the color index of a star, is equal to 0 when the temperature is 10,000 Kelvin. So positive means the temperature is less than 10,000 Kelvin, and negative means the temperature is higher than 10,000 Kelvin. For example, the sun, the B minus V color index is plus 0.6. And it ranges from minus 0.4 for the hottest stars to plus 2 for the coldest stars. If we look at the equation on the formula sheet, we see that the color index, which is the difference between blue and visual magnitude, can be written in terms of apparent magnitude or absolute magnitude. It's the same thing. The color of the star doesn't change with distance. So at 10 parsec, the color index, the difference between blue and red and visual, will be the same as at any distance. Next is the bolometric correction, written as follows. Bolometric correction. So if we think about our visual magnitude, the most commonly used form of magnitude for a star, then it is only a small fraction of the entire emission spectrum of the star. So if we think about the magnitude that represents all of the radiation, there is no physical instrument that is sensitive to the entire range of electromagnetic waves. The best we can do is take a visual instrument, measure the visual magnitude, a blue filter, measure the blue magnitude, and then bring in an ultraviolet telescope, measure the ultraviolet magnitude, and then measure the infrared magnitude, and then take a bunch of points and plot the blackbody radiation curve, and then solve the integral and find the area under the curve, and mathematically calculate the magnitude that you would see if you were able to see all of the radiation. That magnitude is called the bolometric magnitude. So there is no actual physical object that we know of that can see all of the electromagnetic spectrum. But if we could have such an instrument, the magnitude it would see would be what we calculate as the bolometric magnitude. So this is a composite value. We calculate this after making several measurements on several parts of the spectrum. So here's my question. Compare your bolometric magnitude of a star to its visual magnitude. Which one is a bigger number? So write a bigger sign or a smaller sign. Pause the video, write down your answer, and then unpause. All right, ready? So the bolometric magnitude will always be a smaller number than the visual magnitude because this is a subset. Therefore, there is always less visual light than everything, right? And the smaller is the number, the brighter. So automatically, the bolometric magnitude will always be a smaller number than visual magnitude. So when we talk about the bolometric correction, BC, and we define it as the difference between the visual magnitude and the bolometric magnitude, this is always going to be a positive number, always a positive number. And what does that number mean? It is, in a way, telling us what is the percentage of light that is visual, right? If we look at a star like the sun around 6,000 Kelvin, a larger percentage of the light is visual. So visual light will represent a larger fraction. So the bolometric correction will be a smaller number. Less correction is made when you add the remaining of the electromagnetic spectrum. A star like this one at 12,000 Kelvin, the visual magnitude, the visual light is a smaller percentage. Look at this. This is a much larger percentage than this one, right? So you would have to make a larger correction to your visual magnitude when you add the rest of the electromagnetic spectrum. The bolometric correction will be very large. So the smallest value it can have, which it doesn't, is 0, which means 100% of the light is visual. So you would expect a star like the sun to have one of the smallest possible values for bolometric correction, and very hot stars and very cold stars both will have a smaller percentage of visual light and therefore a larger bolometric correction. Now, if we revisit our equations for magnitude scale, you must now refine your equations. Whenever you're calculating magnitudes, you must specify what type. Is this visual? Is this blue? Is this bolometric? And so when you compare two different stars, you must compare the same type of magnitude. The same part of the spectrum is to be compared if you want their luminosities, the ratio in their luminosities, to mean anything. So you can compare visual luminosities, you can compare blue luminosities. Alternatively, you can follow the same star. So M1 and M2 would refer to two different parts of the spectrum of the same star. In other words, vary only one thing. You either vary the star, keeping the same part of the spectrum, or you vary the part of the spectrum keeping the same star. So I could take, for example, this equation, absolute bolometric magnitude, absolute visual magnitude, and the difference will tell me the ratio in visual luminosity to everything luminosity. If I want to do the distance modulus and find the distance to a star, I need to make sure I am comparing 10 parsec and the current distance with the same optical instrument. So the star doesn't look fainter artificially because I am switching my part of the spectrum, right? Okay, to finish up, there is this equation here we did not talk about. This is not very used, but just so you understand, this represents the same object seen after two different exposition times. So let's say these are both visual magnitudes. You observe an object for a longer period of time, especially true when you're using a telescope, and just pointing at the star for a while, you accumulate more and more and more and more light, right? So the star will look brighter if you look at it for a longer period of time, not with the human eye because you're refreshing your image every fraction of a second, but for a telescope, you're just accumulating, and you're accumulating more and more photons on your photographic plate, making the star brighter and brighter and brighter, right? So if you take the luminosity, apparent luminosity, which is basically energy per unit time, and you multiply by the time interval you measured, what you obtain is the total energy accumulated on the mirror of the telescope. And so the two magnitudes, the difference between the two magnitudes for two different time intervals will relate to the brightness of the star multiplied by how long. So this is the ratio of energies accumulated. And that's it.